mean value theorem and some application of this theorem and some other related theorem which is depend on mean value theorem. At first see, what is the mean value theorem? What is the statement of this theorem? Statement of the mean value theorem is, if a function continuous on closed interval AB and function is differentiable, here notice, here the open interval AB, okay, and here since given the function is continuous on closed interval AB, that means function has no break on the graph, and since function is differentiable on the open interval AB, that means there exists derivative at all point of the function in the every interpoint between A and B. That means that implies function is very smooth. If these two conditions are satisfied, then by mean value theorem there exists always at least one point C such that the slope of the secant line on the closed interval AB is the slope of the tangent line at the some point C in open interval AB. This is the statement of the mean value theorem. See this statement by graphically. I have some function and here the point A FA and here the point B AB. This is the secant line, we all of us know. And notice there exists many tangent lines, but there exists one tangent line whose slope is equal to the slope of the secant line. This is the tangent line which is parallel to the secant line. Okay. So, in mean value theorem states slope of the secant line on the closed interval AB is equal to slope of the tangent line in some point C in open interval or AB. That means in mathematically the slope of the secant line, we all of us know, this is equal to, just see the graph, we all of us know the slope of the secant line is y2 minus y1 over x2 minus x1, and this would be fb minus f of a over, sorry, here a over b minus a. Okay, and this slope is equal to, by mean value theorem, first derivative of the function at the some point between AB. Here notice in this graph, this slope is equal to the slope of the tangent line. Consider this point at C. That means this slope equal to would be for A prime C, first derivative of the function at the point C, because we all of us know the slope of the tangent line is the definition of the derivatives. Are you getting the mean value theorem? This is the statement of the mean value theorem. Actually, in mean value theorem, the secant line here parallel to the tangent line, and here the tangent line has the same slope with the secant line. Okay? This is the graphical meaning of the mean value theorem. And here notice one thing. Here in statements has given there exists always at least one point C. Now consider other graph. Consider this graph, and this is the point A and this is the point B. That means this is the f of A and this is the B f of B. Okay, and this is the secant line, we all of us know. Okay, this is the secant line, and notice this tangent line is parallel to this secant line. That means there exists a point C1 between A and B such that this tangent line is parallel to the slope of the secant line. Also, there exists other point C2 such that this tangent line will be parallel to the slope of the secant line. That means in this graph there exists two tangent line at the point C1 and C2 between the open interval AB such that slope of this tangent line is equal to slope of the secant line in closed interval AB. So here has indicate this condition. There exists at least one C. Here notice one thing. In mean value theorem has indicate f is differentiable on the open interval AB. If the function is not differentiable at the open interval AB, consider this graph. This point is A f of A and this point is B f of B. And notice this is the secant line. Notice there exists no tangent line where the slope of the tangent line does not equal to the slope of the secant line. Function must be differentiable at the open interval AB. Okay, notice in option has indicate the function is continuous on the closed interval AB. If the function is not continuous on the closed interval AB, notice the graph. Here at the point B, the value is here. This is the graph of the function, and at the point B, the value of f of B here, not here. That means there exists a jump discontinuity. At first, draw the secant line. This is the secant line, because secant line is joining the point between f of A and f of B. Here notice all the tangent line going through this line. So there cannot exist any tangent line whose slope parallel to slope of the secant line. Okay, so if we omit the condition, if we omit the function is not continuous on the closed interval AB, the mean value theorem will not satisfy. So are you getting why mean value theorem has indicate the function is obviously will be continuous on the closed interval AB, and why the function is differentiable on the open interval AB? Okay. Now I will use some application of mean value theorem. There is some trick. We want some information about the function f, and we have already got some information about the derivative of the function. Then the trick is here we will use mean value theorem. Okay. For example, consider this function. Here given if f prime x greater than equal to 0 for all x belongs to AB, then that imply f is monotonically increasing function. Notice we have information about f prime x and we have to find the original function f, and if f prime x satisfy this condition, then obviously f will be monotonically increasing function. And here I will use mean value theorem. We have to prove the function is monotonically increasing function. That means if we take 2 points x and y, where x less than y, then we have to prove f of x less than f of y. Okay? Consider 2 points a less than x, less than y, less than b. We assume the function satisfy mean value theorem on the interval closed interval xy. Assume function f satisfy the mean value theorem on the closed interval xy. And here mean value theorem will be applied because given f prime x greater than equal to 0. That means function is differentiable on the open interval AB, and that imply function is also continuous on the open interval AB. Okay? Now consider the mean value theorem on the interval closed interval xy. Therefore, by mean value theorem, there exists some point z between x and y such that f of y minus f of x over y minus x equal to f prime z. Let's see the picture. This is a, this is x, this is y, this is b, and the point z lies between x and y. And here given f prime x greater than equal to 0 for all x belongs to AB. That means by this relation we can write f of y minus f of x over y minus x. This is greater than 0. This is greater than 0. Okay? And that imply f of y always greater than f of x. Since I have considered y greater than x and I have got f of y greater than f of x, that means the function is always monotonically increasing function. Okay? That means our proof has done. Okay? Well, similarly, if f prime x less than equal to 0 for all x belongs to AB, that imply f is monotonically decreasing function. Okay? Well, f prime x equal to 0 for all x belongs to AB, that imply f is constant on the interval AB. Are you getting? Try to prove this example own self. Always will apply the mean value theorem. Okay? Now next see the other example. Between the interval 0 to pi by 2, prove the inequality tan x always greater than x. Here I will look this inequality. Okay. Here I will use here the mean value theorem. We all of us know the mean value theorem. This is f of x minus f of a over x minus a, and mean value theorem, this is always equal to f prime c where a less than c less than x. Okay. I will use the mean value theorem on the interval capital A to x, and here I have considered x because I will prove the inequality tan x always strictly greater than x. If you think about this interval, then a would be 0 and x would be always greater than 0 and less than pi over 2. Okay? Well, here notice f of x equal to tan x. This is our given function, and this function we all of us know in the interval a equal to 0 and b equal to x, which is less than pi over 2. In this interval this function always continuous and differentiable also. Okay. I can use the mean value theorem on that function between the interval 0 to x. Okay. So by mean value theorem, here apply, this would be, the value would be tan x because the given function is tan x, and here a equal to, I have considered 0 and tan 0 equal to always 0 over x minus 0. Okay. And this would be by mean value theorem is equal to f prime c. That means derivative of the function tan x at the point c, and this is equal to sec square c. That means sec square c equal to tan x minus 0 over x minus 0. That implies tan x over x equal to sec square c. Okay. And we have to prove this inequality, tan x always strictly greater than x. Now for this proof we have to prove sec square c always greater than 1. Okay. And here notice sec square c means we all of us know 1 over cos square c, and between the interval 0 to pi over 2, the graph of cos square c is this, and at the point 0 the value of the function is 1. That means between the interval 0 to pi by 2, the value of cos square c always would be less than 1. That means sec square c, which is equal to 1 over cos square c, always greater than 1 between the interval 0 to pi over 2. Okay. Therefore, in the interval close interval 0 to pi over 2, always sec square c always greater than 1. Always this is greater than 1. Therefore, from this we can write tan x always greater than x. So our proof has done. Okay. Are you getting the mean value theorem? Okay. Well, thank you so much for watching this video. I hope my all viewers have understood this theorem and application. And this theorem is very important for any competitive exam. See you soon. Stay safe and be positive always.